Hello everybody, my name is Alberto Marquez and we are going to discuss queues or waiting lines. First, let's explain what is a queue or waiting line and why it happens. To begin with, we have a server and that server is waiting for clients to arrive, and we are going to consider that each one of these clients or customers are served one at a time. Now let's consider a hypothetical scenario or a perfect situation in which each one of the clients arrive with a difference of 5 minutes. The inter-arrival time then is predetermined to be 5 minutes. And let's assume that each one of these clients, when they are in the server, it takes the server exactly 4 minutes to serve them. No changes in the time in between the arrivals, no changes in the service time. And when that happens, intuitively you will know there will not be any queue, because as soon as the client enters, then the server will be free. It will take exactly 4 minutes, and after it's been served, the server has 1 minute idle, and then the next client arrives. And under those circumstances, if there is no variability, then there would not be any queue. But that would mean a perfect world, kind of a clock type of work. Now imagine that for some reason the clients cannot make the arrangement to arrive with the exact difference of 5 minutes in between them. If that's the case, now we have a situation in which 2 or more customers could arrive at the same time, or close, not exactly the same time, but very close one to another. And if that's the case, then one will enter to be served, and the other, the second one who arrived just a fraction of time later, they will have to wait in line. And while that happens, as soon as the first client leaves, the server does not have any free time, so immediately has to start working on the next one. And if for any reason in between those two comes another one, because there is no coordination between the clients, and another client arrives, then the line begins to form. Eventually, because the service time on average remains 4, and on average the time between arrivals remains 5 on average, eventually the server will catch up and there will be 0 customers in the system. But it's just a matter of time before that situation happens again. The situation in which there are clients that are waiting in line. And that is just if there is no coordination in the arrivals. Imagine that we add now the additional noise of having variability in the service times. If we have variability in the service times, now it is even more likely that we will have waiting lines, because even if some customers arrive almost every 5 minutes, but some of those customers might take a little longer than the regular time, and some of them might take fewer time, nonetheless those that took more time, chances are will start to generate a line because the server was not available. So the lack of coordination between arrivals or the fluctuations in times of service promotes these queues. Now, there are certain rules that we can consider, like, for instance, customers could decide to leave the line if they are waiting too long, etc. But this moment, let's just consider this is the simplest of all the possible service or queue systems. And here in the image we have the picture a little more complicated with multi-channel queuing model, in which, although we have a single line just before the clients it is about to enter into the servers, the client will pick probably the server that is available first, and after that the clients go flowing through maybe the rest of the facilities. So this is a multi-channel model. In queuing systems, we need a notation to explain what is the situation for which we are referring. And we have, the convention is to have a certain number of spaces, at least 3, separated by a diagonal. And the first 2 spaces refer to the inter-arrival time for the first spot, denoted here with letter A, and service time distribution for what is denoted in the second space, or letter B. And the possible values for those are m if the distribution is exponential. The reason why we consider it m, or the reason why it's used m, is because it's a Markovian process. We can use letter D to denote deterministic distribution or deterministic behavior, which means that basically there is no randomness in the process, which is the ideal of the cases. We have an airline type of distribution, airline type K, if we denote with letter E. And then we have other type of distributions, mixture and phase and general. The other parameters that we have is the number of servers in the third spot, the restriction on capacity in the fourth spot. And what we mean by restriction of capacity is if you have 3 servers and you can make a line of up to 5 beyond the 3 servers, then the capacity of the system would be 8. 3 in the number of servers plus 8 in the line. We have letter C to denote the discipline. By default, we consider first come, first served, but there are other disciplines that we could be using, like for instance, last come, first served, random selection for service, maybe some priority or other general discipline. So let's see some of the examples for the notation that we may have. The simplest of all the models would be an MM1, in which we have exponential time between arrivals. We would have exponential service, and we would have 1 server. There is no limitation of the number of clients that could enter into the system and be waiting in line. And since it's not denoted, the default is first come, first served. Another example would be MG511. This means that the inter-arrival time is exponential. That means that the service time is a distribution, as a general distribution, not specified, but is probabilistic. We have 5 servers, and because the capacity is 6, we have up to 6 clients can wait in line. Here we have another notation, which we have G and 4 in brackets, G and 10. And what this means is that there is some distribution for the time between arrivals that is not deterministic, but we cannot guarantee that it's exponential. We have some distribution for service, and we have 10 servers. There is no limits on the number of spaces in the line. However, the arrivals happen in batches of size 4, and that changes the behavior of the system. And then you have other type of situations. As we said, the clients could walk out of the queue, and there are other situations. Now, the reason why we measure these, we're interested in queuing theory and queuing systems, is because we have the capacity to have performance indicators or measures that interest us. So here we are going to discuss some of them. We have L denotes the length of the system, and that implies how many people are in the queue plus how many people are in the servers. Associated to L, we have LQ, which is just the length of the queue, how many people or how many customers are just in the queue without considering the number of clients that are being attended in the system as expected value. W is the average time in system for any particular client and as an average, and that includes the time that it was spent on the line plus the time it was spent being served at the server. We have WQ as the average time in queue, which is just the average time that any particular client would expect to be just in the queue. We have the arrival rate, which is the number of clients per unit of time that arrive into the system. We have mu, which is the service rate, or the number of clients that any particular single server can serve per unit of time. C is the number of servers. Rho is the utilization of those servers. Pn is the probability of having exactly n clients in the system. The simplest, or to start with, if the system has no client, that would be P0. And in a model with only one server, P1 would mean there is one person, one client in the server, and there is nobody in the line. So, and so on and so forth. R is the expected number of customers in service. So some of the general results that you can use regardless of the distribution that we have obey to common sense on the behavior of these indicators that we have. First, Rho, which is the utilization, is always the arrival rate divided by the number of servers times the service rate. So the more servers we have, the faster we can serve them, the smaller the utilization, the higher the arrival rate, the higher the utilization. L, which is the length of clients in the system, the total number of people in the system on average, that is equal to lambda times W, where W is the average waiting in the system and lambda is the arrival rate. Similarly, the number of people in the queue is equal to lambda times WQ, which is the number of people in the line equals the arrival rate times the average waiting time just in the queue. Naturally, the time that we spend in the system is equal to the time we spend in the line plus the time we spend being served at the server. And if the service rate is mu, then the time we spend in the server is the reciprocal of mu, 1 over mu. The probability of finding BC the system is Rho, which is the utilization, and it's again lambda divided by the number of servers times mu. R denotes the number of servers that we will find BC and steady state, and we just divide the arrival rate by the service rate. Again, the service rate is the service rate per server. And just like we did before, the number of clients that we find in total in the system are either in the queues, which is the number of that we find in the queue itself, Q, plus the number of people that we find in the servers. So L equals L. And finally, the number of people, when we're interested in finding no one in the system, we denote that as P0, or P sub 0, and then this is computed as 1 minus Rho, because Rho is the probability of finding it BC, then 1 minus the Rho is the probability of finding it idle. I'm going to stop here, and I'm going to continue in another video.